Thank you for the invitation. It's really nice to be here. And I really hope I give you something for your time spending here. So my name is Thorngren. I am doing robotized autonomous vehicles. And it means that I am working for Volvo Group. Volvo Group is the second or the biggest manufacturer of commercial vehicles in the world. We have a number of brands, such as Mack Trucks, Asia Trucks, strong links with the UD Trucks, and obviously Renault and Volvo as well. We run our business in roughly 22 different operation domains, like mining, like forestry, and so on and so on. And the main thing for this presentation will be our hub-to-hub robotized autonomous vehicles. I've been doing this for a few years, started actually in 1990, so it's a long time ago. Started development in 1980 actually, so it's a long time. The product I will present to you is the standard vehicle autonomous trucks, which is basically our take on how we provide technology for companies that actually provide the autonomous stacks. So this this presentation will not focus on radar or sensor fusion, the traditional AD stuff. It will instead talk about how do we make a truck safe and working, and what kind of mitigations or what kind of principles do we apply to the truck itself. Because the truck itself needs to be adjusted quite a lot in order to be part of a safe environment for autonomous system. So we need to provide redundant computational. We have communication, motion management systems, power management system, brake system redundancies, steering system redundancies, and a lot of other parts that we need to change the vehicle to make the vehicle safe enough to mount an autonomous system for the AD driver. What we figured out is actually that for a number of applications, we don't even need the autonomous system part, because we could use many other technologies and do not need to rely on radar and other technologies. And I will come into that later on. So it has been an eye-opener for us to have this perspective. For us, we need to secure our front axle steering systems, our electronic brake systems, our air pressure management systems, our IU systems, our vehicle computational systems, and our power management systems, and then the engine systems. They are also actually changed because we have a different power consumption in the vehicle due to the much higher power loads of this vehicle with additional alternators and similar. And then obviously all these things together makes us provide a test system that is able to monitor all this together. When we bring everything together in one truck, that truck is by far the most complicated vehicle as a truck that's been produced so far, due to all these dependencies on all these different systems. Just to give you a slight hint on the amount of changes that the truck has to undergo, we could just open the hood. So we have opened the hood, and you see the right side of the hood and the left side on the hood. And you see that we have a completely, this is the steering system in truck. If you don't know that, that's the steering system. You have a similar on the other side. So we have then dual steering system in the vehicle, and we have dual alternator systems, and we have a completely new way of doing the boosts for the air pressure management system. So it's a very, very big change in the vehicles to make this happen. In addition to that, we created a new way of deploying our software through our digital twin systems. So this is basically the view of the person downloading new software in the vehicle. So this is the point where he selects different types of software. And those are the nodes over there where we deploy the different parts. And that's rack mounted. Obviously, it's not normally open like this, but you see the rack in the lower parts here. And you could see that everything is stacked up so that you can remove the different computational nodes and replace them. It's probably, or it's super likely that the truck will be on the road for many, many years, but the computers will be shifted gradually as the system matures. So to do this this type of systems, we have following this path, sort of, to understand what's happening when we develop. So first thing is to make an observation on how do we test automated robotized solutions. Yes, they bring complicated stuff, but they bring a lot of opportunities. So it's not only problems. There are many possibilities with this type of systems. So basically, we are all over the board here. We have our traditional L1, L2 vehicles that operate in a traditional way. And we have the Teslas on the 3 level, but our focus is mainly on the 4 and 5 level, where you either have a limited support from driver by or no support at all. So that's how they look. So from a test or integration perspective, the truck offers very good possibilities in this setup. In the traditional setup, we have a driver controlling a vehicle, and that driver is also the extra sensor on the system. He will detect steering failures, he will detect power measurements, power problems, a lot of things that the sensor systems in the vehicle itself doesn't detect at this point. So we need to see how do we replace the driver in all its aspects, with diagnostic, with synthetic sensors and so on. But the really big benefit here is that we have then introduced a generic API in the vehicle. So it makes the full operation of the vehicle programmatically doable. And for a tester, that's a dream come true, because it makes it possible to completely control the vehicle in all its aspects through the API. And that means that our test ability is much higher than it used to be. So it's a problem, or it's a challenge with the autonomy and the robotization, but it's a huge benefit from a test perspective. So we are shifting over from traditional testing and development methods where you have a driver telling you what's happening in the vehicle, and instead you have a vehicle connected, remotely controlled, and the test leader, actually that's me, is seated on a test track and operating vehicle through the APIs to learn and figure out through exploration how the system works. So this is something we really have tried to use and be efficient. So we started to develop a number of test systems to take to bring this possibility into vision and have a solution on that side. So this is basically how our vehicle started to be operated some years ago. So you saw the picture of the ongoing tests, and this is basically what the test leader, equal to me or my colleagues, would see. You have a control system to the left where you see different parts of the system depending on what you're working with. If it's pneumatics, you will see the pneumatic system. If it's steering, you'll see the steering system, and so on. We use gaming system in this setup. So basically, me as a test leader, I program my own interface and I deliver it immediately. So the lead time is minutes to change the system. And we then use Steam Deck controllers or similar to engage and disengage different parts of the system. The technically most advanced part in the system is the top system, which is the onboard tests. And that's the hard thing to make happen. It's a rule-based system that executes 30,000 to 40,000 rules per millisecond. So it means that our test capability is in the millions during a single test session. So basically, this is how we explore the system. So then obviously we need to mount a lot of different switchboards and similar. For example, this is the redundancy control systems for all the different systems. So it looks a bit like an aircraft in the end. And there could be many more switchboards. And then we have different safety systems that we're using. In order to mount all the equipment needed in the vehicle, we have racks in those trucks. So basically on the top, you see the major logging system, logging about 36 different channels. Could be more, depending on the specialty usage of the vehicle. And then you have the analytic systems, and then you have the gyro systems. And then on top of that, we have the vehicle control system that enables it to be remotely controlled or local control. And then we have a number of different power systems. And then depending on application, we add on other measurement system for that specific topic. And we use basically 5 different communication systems. We have up to 9 networks in a single vehicle. So it could be controlling a video link through 5G layered. So it's not what you have in your mobile phone. This is only an icon when it says 5G. There is no 5G, but this is true 5G, where you have a layered communication with different communication layers. We do similar with different kind of drone networks like DJI or similar. And we use for positioning in environments that lack networks, LoRa. And we also control the vehicle through fiber systems. So it's a fiber control vehicle. And that's used for EMC, but it could just be for other applications as well. So how do we then do the actual testing? Yeah, I showed you the onboard vehicle autonomous driving equal to you have the tester in the vehicle. Obviously, you could have the tester outside the vehicle at a test site or a truck control center. And the third one is that we have we build up scenarios depending on the needs for different teams. So we generate a certain scenario driving for brake stress testing or brakes. So then we receive those and create those scenarios. And then we create, this is the exploratory tests method with the test driver seated controlling the interfaces, exploring, seeing the usage of the autonomous system. And it gives you an extremely good insight very fast in what capabilities the autonomous or robotized vehicle has, because you're pretending to be the autonomous system. You're taking the role of the autonomous system. So you could detect how the system brakes or how the system steers yourself by steering and driving. So it's a very efficient way of getting an understanding of the system. And then we have the robotized testing. In this case, it means that we have an arming system that arms the vehicle. So the driver gets into the vehicle, turns on the key, arms the system, engages the system, and then steps out of the vehicle and secures that the proper test methods have been loaded in the vehicle, and off the truck goes until we run out of diesel or the program is the test sequence. So this means that we can have test vehicles up and going so much more than we used to do before, because we can automate the full testing. It's fully automated testing. And then we have also different numbers of remotely operated solutions, and that could be at fairly high speeds because we are controlling networks. Here we are changing the traditional way of seeing a vehicle as being the sensor base. Normally, when you build this type of vehicles, you mount everything on the vehicle. Here we're doing the other way around. The vehicle is fairly stupid, but the road is very intelligent with cameras and radars. And it means that we could take base vehicles and test them. And this is important for us because autonomy and robotized is not bringing money today. It's not the cash cow of today. So we need to prove that we could use these technologies for other track applications and then combine traditional truck development with this. So it's very important to be able to support non-autonomous robotized testing. The cornerstone is obviously the log system, one of the cornerstones. So as I said, it's mounted here. It's basically it's super simplified, but it's time synced on Ethernet level, controlling the time in the complete vehicle with a number of different sensors. The value of this can't be underestimated. So it creates enormous volumes of logs, obviously, that we then need to deal with. And we do that through automated checks. So we have the automated rule-based test framework as the foundation, and then we scale that up with AI application. But the basic principle is a rule-based system. If that is true, that can't be true. If this is like this, if we're driving, the light should be on. If we are braking, the brake light should be on. Things like that. I mean, simple rules. So they are then described as state machines, and the state machines are then loaded in the truck, and then they are monitored. So this is a typical code. The state machines are, to be very fast in execution, they are written in C++. But obviously, you could use other languages to generate the C++. But the execution is the C++. That's why we could have these 30,000 per millisecond or even more And then you see typical log structure from an engine, and then how that is dealt with by the test structure. So that's why they are, and we have 34 networks, so there's a lot of networks to be picked, and they all need to be time synced. So you could see that, yes, the gear shifting happening in CAN 5 or something is engaged by the vehicle control unit, and it's understood, or the steering signal from the autonomous system is propagating correctly through and engaging both the primary and secondary front axle steering systems. And to do this, we also have a number of control systems that are managing the test fleets. So we are assigning teams test fleets. There's truck on the top, different trucks. There's a lot more, but we have more than 2,000 trucks actually. But this is typically the control system, and then you could see the deployment of different software packages to the different trucks, and it's fully automated. And then it's also linked. This is the fully automated feedback loop of the configurations, because this is built into a CI/CD flow. So when the software is developed in different teams, they hit the different software systems. And I think we have a roughly 17 million versions upcoming out. So it's fairly big numbers. And the version you saw before is then fed back so that the digital twin, that the integrator who's deploying the software can see that and understand that did my software come into the truck, and then act upon it. And actually, the full process could be completely automated. So the only thing you, this person, needs to do is to secure that everything is operating correctly. And then you get different type of feedback loops here. So you can see the vehicle you saw before, is version there. So that's the name of the vehicle and the version of in the digital twin system. And then you have the functionality here, different functions. And for example, something super simple is direction indicators. So we tested that 49 times passing and 6 times failing, because when you have this type of system, how often do you test something in the vehicle? How often do I test the brake system? I test it every time we brake. So my test coverage is 100%. Every single function is always tested. So because I have all these capabilities and all the systems. So here we see 6 failings, and then they are queued into an event log for the teams that need to deal with the events, and then they steer out the issues to the teams, and then they need to act and then redeploy. We are also using these systems to discover the system. In this case, this is how we discovered the alarm activation, deactivation, linking between different functions. We have roughly 3,500 different functions in the truck. So how do they relate? If I change this function here, fob, key fob, key fob, will that affect windows, power windows? Yes, it might. How does it relate? And that's something we calculate through the systems, because they are basically impossible to figure out just by pen and paper. There are so many complex dependencies. So that's the check system that we're using. But the focus in my work is to be as close as possible to the truck itself. Get rid of as many PI plannings and meetings and things like that, and spend the time in the truck, because that's where we could get the data and understand the reality. So we then have a number of what we call pit start teams. They are organizations, mechanics, electromechanical engineers, and software engineers that are based on the test sites, and they just to secure that the vehicle is up and running, so it could take data and provide new test data. And it's a very traditional truck work in many ways, although very, very IT intensive, but it's still gear shifting, wheel maintenance or deck shifting or fluid oil or steering oil or something, steering fluids, sorry. So typically, this is the old Saab facility. Saab, if anyone remembers the car brand, perhaps you do. This is their factory, and this is their former test track. It's been not used for 18 years that we started using it. So we have a facility, one of our teams, we have a few test sites. And then in that building, the test team is mounted, is working, sorry. And then some trucks are then using this space to provide the data and then deploy new software and then provide new data and deploy new software. And for higher speed, we are using the high speed area to do the same. This method has then been deployed on our other test sites. And I have a dream to have that also for our US test facilities, but that's not in place today. So typically, how we test. So the thing I wanted to show there was actually that we connect them to Teams. It could be done with Slack. So we have one channel for each truck and each application. And then the teams that belong to that application, brake teams, belong to brake. When we do brake testing, they are notified in Teams that this is ongoing. And then the Bangalore team, for example, or the Curitiba team could join in the team channel and in real time see the testing and give feedback to the driver. They can also retrieve the logs in real time, so they don't need to go to the truck to get and they can also deploy the tests not only to the test trucks but also to the production trucks. So it's so how do we build confidence? We build confidence by having the vehicle in usage, and we have like boxes here, certain amount of mileage combined with a certain amount of operations. And the more operations and mileage we are gathering without seeing any type of issues, and we are measuring every part of the system, then we climb up in maturity steps in the vehicle depending on how long. You follow me? So the first box is low speed, 50 miles, 50 test iterations, and then we go up in time, and then we go up in speed, and then we enter new boxes from a safety perspective by having the system secured. Obviously, if we fail, then we fall off in boxes and have to go back in boxes. So that's the testing on tracks. Conclusions. My general perception of doing these things is that the most important thing I've seen, and I've been working for like 4 years actually, is that the key process to have under control is your build, measure, and learn process. This is the key thing. And that's why we have automated all these types of by being super fast at building a new system. We could do that in minutes, actually, and then get it into the product and then start the measurement systems. We are generating data, and we could immediately learn, not go into processes or PI planning, so whatever you do, stop that. Instead, be close to the product and then act with very, very high frequency on how you're working. And then there's a very, very important to understand that we don't know very much. So we must be in this world with the general perception that we have a very limited knowledge of the systems that we're working with. So we must accept uncertainty. So we need to deal with that. And I call this the safe zone of the product. We know about the problems, and we have regression tests. I have those checkers in place. I will not miss that. That's under control. So we need to get this area bigger, and we do that by exploratory testing. That's why I have the steering wheel. I explore the system, I learn new behaviors, new things to take into account to move them into the known state where we have regression control. And then we work with simulations. I'm not at all, simulations are super important. I didn't bring it up in this presentation because that would take too much time. But that's another domain where we have a similar approach. They figure out other things that we need to deal with, and we need to move them into the green area to get out of the danger zone, things that we don't know about, and make this as small as possible. So that's the perception of how we do it. To bring automated product to market, you need to automate. We need to automate the complete process. So it's not only the autonomous trucks that needs to be automated, the product development process itself needs to be automated as well. So that's about how we do it today. I have a video, but I'm not sure if we have time for that one. Yeah, so this is from our test sites in Houston and Austin. So this shows it for real, I hope, at least. Who knows? Might it start? No, it did not. I don't think I have network connection here or something.
Yeah.
It is? Okay. Let's see if it stores. Yeah.
Go to YouTube.
Oh, is he connected to Wi-Fi?
It is connected to Wi-Fi.
But it's not playing. Anyway, there are millions, not millions, but at least a lot of clips on the internet, so you could see all the stuff there. So we could use the time for questions instead.
Yeah. Thank you for the presentation. Any questions? Yeah, go ahead.
Yeah, thank you very much for this presentation. Really impressive with the speed, all the things. I had a question regarding deviations and your quality things. So, are there some deviations that your digital twin and model behaves differently than the truck, or how do you handle them, and what kind of deviations are those?
Yeah.
I would be interested to see where the risks are and where we can improve in future.
Yes. There are always. There is no way at all. Just forget it. It will never be that your digital twin is equal to your physical system. So just accept it. Obviously, we need to keep them as minimal as possible. But to give you, we have some contact with the defense systems, and they have aircrafts, and they synchronize their virtual reality with the reality. And if they keep those systems in sync for 30 seconds, they are super happy. Just to give you an understanding of how hard it is to get those two in sync. That's why it's so very, very, very important to get into real systems with real tracks, real air, real snow, everything. Because there is no way you could simulate all that. No way.
Theoretically, I know all the difference, but practically, I don't.
Yeah. So I'm not disputing the value of simulations. It has a great value as long as you understand that you can't do more than what's possible in the box, and you need to link your simulations constantly with the real world, so the real world is feeding data back. Then that's a perfect. It's a must-have simulation, obviously. I just don't have it in my presentation. That's why I'm not talking about simulations. Sorry. Yeah.
So I was wondering, for the track testing.
Yep.
Is there a specific ratio between the physical miles that you drive on a track and the virtual miles?
Everything like that is really hard to measure. So in order to when I work with quality, I first obviously you could look at the component quality. Can you conclude anything from the components? And you could get some insights from the components. But the real value of how valuable your component testing is when you come to the system. Because if there is a really, really high value of the component testing, then you could sort of probably scale down on your system testing if you're really, really, really strong on the component testing. But equally, that goes then to the real system testing on the track when we drive, and then we compare that with the simulation systems. And today, I would say the value of simulations are not super high, actually, fairly low, I would say, because it takes a lot of time to get those systems in shape. I was the global verification and integration leader for our launches in the 2010s. And it basically took us 3 years to have valuable simulations in place. It takes a lot of time because you need to run a lot of mileage. Then it's really important that you have deployed something similar in your customer vehicles. So we already have the same log system measurement systems in the customer applications or the partner applications. So then we could validate, are our tests and assumptions correct? Do we see the same things? Have we failed on something? If you're failing there, our test time is too small or too low, and we need to increase that test time. So you need to balance all the time how much goes to components, how much goes to system, and how much goes to simulation. I'm not sure if the answer was to the point. So the answer is, I don't know.
We have 2 more minutes and then we're done.
So I wasn't totally sure I followed what you meant by your exploratory testing in this case. Were you essentially pretending to be like the brain of the autonomous system?
Yep.
Just using only the interface
Exactly.
the system has available?
Exactly.
Okay.
Precisely. And it gives you, it's fantastic how much you could explore by that. For example, you'll be driving and then you disengage the primary steering system, and you see behaviors I haven't seen that before. and then you disengage the primary brake system, and then you see completely different behaviors. And then you could shut off different parts of the computational system, and suddenly we have a very, very different behavior. I don't see any way of sort of simulating that in a valuable way, because it's far too complex in a vehicle with 76,000 internal signals, 30 networks, and figure that out in a spreadsheet or something. So explorer testing is very, very important.
Sure, thank you.
Yeah.
I think we'll conclude the discussion because you are here. Yeah. So you are here for
Yeah,
tomorrow. So
yeah,
we'll find it after this session. Thank you.
Thank you.
Thank you for the presentation.
Yeah.